So welcome everybody and welcome back. This is session 8B. You can see the QR code at the bottom left. Please use it to leave feedback. John has asked for questions throughout the presentation, so I'll be keeping an eye on that. Take it away, John.
Okay, thank you very much, Martin. So good morning to everybody. I will turn off my video in a second. I just wanted to make sure you could see who I am. So let me just do that right now. And that should be off. So my topic for this session, as you can see, LPARs, weights and processes. I'd like to look at how we define our LPARs and what the results are as far as processor efficiency, how we can look at that, i.e. what SMF records there are, and not only how we can change it, but what happens when we change it. So I'd like to really focus on that topic and give you the feeling that looking at this information means that you can understand what's happening and also modify it for the purpose of improving the efficiency and letting the workload run faster and getting more done. Okay. So agenda, just quickly look at a couple of things like how you define an LPAR, just very general things. I would like to touch on the processor topology. That means for a particular architecture, what it looks like for a processor as far as cache and chips and what it's using, because that comes into this discussion. We want to look at the usage of an LPAR, the resources, not only how much is being used, but how efficiently they're being used. And then we want to look at, okay, what happens when we change it? Firstly, how do we change it? And what are the results? What are our expectations? And what is our target? Okay, so I work for IntelliMagic, based here in the Netherlands. I'm a senior consultant. And just quickly, we look at a lot of interesting information in performance capacity. We're based in the Netherlands. We do have offices in the US and in Germany. We work with a lot of people together, and there's just a quick indicator of who we are and potentially what we do. So that's it on the company. Let's move to LPAR definitions. Before I start, I need to make some assumptions. I'm trying to keep it simple, which means that, for example, I'm not looking at all your LPARs with group capacity and things being capped, okay? That's a different discussion. I'm not looking at, for example, somebody who uses IRD to dynamically manage the weight of LPARs, okay? So what I'm looking at when I look at an LPAR weight definition, I'm looking at the initial value, okay? I'm also assuming that we're using logical processes, i.e. hyperdispatch equals yes. Another assumption is that in your installation, you're not using something like TFP hardware consumption, where you can change the amount of MSUs you have available. Okay, so there are a lot of assumptions here, but we have to start simple as far as I'm concerned. I will be looking at reports in RMF, but also in our product, which is called IntelliMagic Vision. Sometimes it's easier to see things visually to give you an idea what we're trying to look at. And I'm also looking at general processes, CPs. Now, what I'm talking about is also very relevant for zip processes, okay? But as I said, I'd like to keep things simple in this presentation and give you an idea of what to look at and how to modify it and what to expect. Okay, so let's start with the LPAR weight. You have a KEC, a mainframe, and you've defined your partitions, ZOS LPARs, and you assign a weight to each LPAR, just a number. And the weight is used when we look at the relative weight, i.e. this LPAR compared to the others defined in that KEK, it's used in order to carve out the resources that we want for that particular LPAR. So the LPAR weight number is really used just to work out the relative amount. You can see on the left-hand side, we have weights defined in the second column, and the total weight is 300. The relative weight I've calculated. So for LPAR CIS1, the relative weight is 8%. I find it easier if the numbers you use in your definitions are actually a factor of 10 or 100. Then you can understand the relative weight by what you're typing in. That's just a recommendation to make life easier. So what we also have is processes that we define for our LPARs. And we're talking about logical processes. So what's important to understand is that when we define our LPAR, we define the number of processes, but we can actually vary processes offline during particular times or at all times for that LPAR, okay? So they don't need to all be online. Now, as you see in this chart here, we have these 4 sample LPARs with their relative weights, column 3. And in column 5, we have the logical processes that we have assigned to that LPAR. Okay, so LPAR CIS1, we assigned a weight of 80, which works out to be a relative weight of 8% of the resources. And we want 5 logical processes assigned. This particular KEK has 33 processes. And if we look at the sum of all logical processes for LPARs, it's 43. Much larger. Okay, we're sharing processes. That's clear. Now, column number 4, I've labeled CP share. That's the percentage of processor share based on the relative weight that you've specified. And we'll get to that a little bit further because that's a very important thing to look at. Okay. So there is a recommendation from the Washington System Center that the number of logical processes you define to your LPAR is 1 or 2 more than the CP share. Okay, so you can see here that the calculated value, column 4, CP share, is less than the logical processor value, column 5, that I've assigned, 5. And it's 1 or 2, it's a little bit more than that. Sometimes I see LPAR definitions where customers have defined very, very many logical processes in the hope that more is better. That's not the case. So be aware of that. Look at that CP share, and we'll show you how to look at that value, and then look at the number of logical processes you've defined related to the CP share value. So another interesting and very important thing about logical processes is a logical processor has a polarity. So I've defined a few more columns in my table here on the right-hand side. VH is vertical high, VM vertical medium, and VL vertical low processor polarity. So we're talking about the share of the processor resources. So the vertical high, for example, is almost like a dedicated processor. And I'll get to a little bit more describing how these processes are defined for the LPAR and what it means. But we're basically talking about the sharing of the logical processes for the LPARs. So let's look at the processor topology. So what do I mean by that? The polarity is vertical high, medium, low. So a vertical high processor is basically dedicated. 100% processor dedication to this LPAR, let's call it that. A vertical medium processor can be shared and will be shared between LPARs, and it's between 50 and 100%, somewhere in that range. And then we have vertical low processors, which are much smaller, that share value, and are shared between LPARs. And when they are not being used, they can be parked, which means they don't use any resources. So if we look at our sample LPAR sys1, 5 logical processors, what we have, and I'll show you how it's being defined, we have 2 vertical high processors, 1 vertical medium, and 2 vertical low. Okay, so that's interesting information about the processor polarity. But what does that mean as far as efficiency? And that's why I'd like to look at the processor topology, and as an example, the Z15 architecture. So let me look at a single draw. On the bottom left, you'll see what I've labeled PU processor unit number 1. So that's our processor. It has a dedicated level 1 cache, a level 2 cache for that processor, and it is sharing a level 3 cache, and of course a level 4 cache and memory. Okay, so the instructions for data, this is where it's stored, and this is where the data is dragged in from to level 1 so that the processor can actually do the work. We look at the architecture and we expand it to the chip, which in this particular architecture includes 12 cores. Each of them has their own level 1 and level 2 cache, and they're sharing the level 3 cache, okay, and the level 4 and etc. We go further in this particular architecture and we talk about a cluster, which is 2 chips, and you can see it visually here as well, okay? And then we talk about a drawer, which contains 2 clusters, okay? So we're building up our image of the processor topology in our current architecture, Z15. And that is a single drawer, and with this particular architecture, we can go to 5 drawers. So this is what it looks like. This is another way of looking at it from our product. And what we're looking at here is a sample LPAR, E001, and we're looking at the CPs, which are 0 through A. We're looking at the polarity of those CPs, vertical highs, medians, and 3 vertical lows. And they're all placed on a particular chip, chip 1. And we also have zips, which are also placed on particular chip or chips. Where do we get this data from? The data source is the SMF 9914 hyper-dispatched topology. Very interesting information about what our LPAR looks like and where these processes with their polarity reside, which means what cache they actually get their instructions and data from, the hierarchy. Now, for our particular case, we also use the RMF 70.1 processor activity records and also the hardware capacity records from the SMF 113 subtype 1. So what are we seeing here? A little bit more detail. So we have 6 chips assigned to this LPAR, and we see that their polarity, highs, medians, and lows. And we see actually that they're all sitting on the same chip, chip number 1. That's why I have a thumbs up saying, great, they're sharing the same level 3 cache. By that, what I mean is whether the workload runs on processor 0 or processor 6, the level 3 cache is the same, which to me is an advantage, okay? The specialty processors, the zips, are also defined here, and in this case, they're spread across 2 chips. We can see that processor number 6 is on chip number 1, which is the vertical medium. So we're expecting that's the bulk of our zip workload. And for this particular LPAR, we have 3 vertical low processors, and they're all defined on chip number 2 in a different cluster. So that's why I have a thumbs to the side saying, okay, maybe that's not ideal, but that is the way it is, okay? Just as a side note, we can see that we're using SMT for these processes. So processor number 6, logical core 6, has logical processes C and D, okay? So we see this kind of information in the topology data that I told you about. So this tells me, for example, that the vertical low processes that I'm seeing, both the CPs and the zips, I'm hoping that they're not being used very often, especially the zips, because they're actually in a different location as far as the architecture is concerned. And we'll verify that in a second. Now we have to remember we're looking at one particular LPAR on this KEK, and it looks different when we look at all the LPARs defined, and we'll have a picture of that in a second. Okay, so how does all this hang together? So we started with the LPAR weights. So let's look at that. I'm using an RMF report here, SMF70 type 1, the process and partition measurements. In the left, you will see what we see in RMF with the partition names. And in the right, I've just placed that into an Excel table for us. And our example LPAR is E001. That's partition P1 E001. We can see the weight that we specified in the console and the relative weight that that represents. So what we can also see in this data source, SMF70 subtype 1, is the CPU activity report, where we can see our 6 logical processes, and we can actually see the current processor polarity for that interval. It may change. Be aware of that. Okay, so we can see there's 1 vertical high, 2 mediums, and 3 lows. And we saw that in the topology view as well. Okay, so let's take a look at what we set and just confirm that that's what we are actually getting. So LPAR E001, the KEK has 33 general processes. The CP share, well, it's the number of general CPs, and it's the percentage, i.e. the relative weight, and it works out to be 2.49. That's straightforward. So here it is in my table, 2.49 CP share. Based on that CP share and the number of processes, we're going to get a vertical high, medium, low split, okay? So we're going to get 1 or 2 vertical mediums that have at least 50% share of a processor. The remainder integer value of that CP share is going to be a vertical high. And then what's left are going to be vertical lows. Okay. So that's the way it's described. And we can calculate this as well. So to make life easier for myself, I've had these formulas for Excel, which you certainly should try to use yourselves, where we can calculate based on the relative weight and the CP share for that KEK and the number of logical CPs we've defined, what the vertical high, medium, and low processes and the numbers are going to be. And in this case, yes, it matches the RMF report. That's good. That's what we hope for, and that's what we expect. So how can we observe the usage of the LPAR? Well, what do we want to look at? I'd like to look at how busy the LPAR is, i.e. the MVS logical resources. And also actually the LPAR resources assigned to that MVS image, i.e. the KEK resources. So what's interesting to me as well, is that within the limits that I've defined, or is that MVS LPAR using more actually than I'm expecting and want it to? That's an important thing that I think we need to look at. When we have peaks in our workload, in our resource usage? How bad is it? I think that's a good thing to look at as well. And then the question is, okay, what could we change? What should we change? And once we've done it, how can we look at it and verify that that was the right thing to do? So they're quite interesting topics here to look at. So how busy are we? What we'd like to look at is MVS busy on the left and LPAR busy, both sourced from the SMF 70 subtype 1. So the MVS busy shows us basically how much CPU do we need for that logical partition from the MVS view. The LPAR busy is telling us the actual consumption of the logical processes, i.e., do we have enough capacity from the definition from the Keck view? That's how I view these two charts. So if we go back to an RMF report, CPU activity, one interval, we can see, for example, the LPAR busy for those 6 processes and the MVS busy. So if the LPAR busy is below MVS busy and often below MVS busy, that's telling me that, well, actually MVS needs more resources than it is assigned. And okay, so we need to maybe look at things like the weight, the relative weight for this particular LPAR. Okay, so that to me is the first indicator, okay, I need to look at something. What we can do is then look at the MVS busy and the LPAR busy together in a chart. So MVS busy is the red line, LPAR busy, i.e. the resources, is the blue line. So yes, MVS busy is often higher than LPAR busy. So I'd like to look at this LPAR closer and make changes potentially. So my question is, well, I have defined resources. I've defined a weight, which works out to be how many processes and what a cut. How are we using that relative to our definition? So what we're looking at here is what we refer to as the relative weight versus the CPU usage relative to the LPAR weight. That means, are we using more CPU than what we defined in the LPAR definition, i.e. in the weight? So when we get peaks above 100%, it means, yes, this LPAR, this MVS is getting more resources assigned to it than we actually defined and want. It's getting them because the other LPARs aren't using it. So maybe that's not an issue, of course. But as far as the definition, yeah, this doesn't match what we want. So for me, this LPAR could potentially benefit from an LPAR weight increase, a relative weight increase. When we have peaks during our processing, how bad is it? And we have good data available also in the 70 subtype 1, which shows us the work queue depth, which means how many work units are ready to be dispatched, but not yet, okay? i.e. what's waiting, but ready. And they're put into separate buckets. So we can see it visually here. When we have a peak, how bad the peak is. And we can look at that together with the RMF report. And let's look at one interval, 11 o'clock. That was one of the peaks. So on the right-hand side, you see what we see in RMF. We see the buckets. And we can see, for example, the bucket n plus 10, okay, and up to n plus 30. That's where the bulk of our work units are sitting and waiting. So this is typical for peaks. You'll see that things are waiting to be dispatched. And the question is, how bad is it? Now, one thing you have to be careful of, my observation is that in very large LPARs, in many processes, you'll see that the peaks have many larger occurrences of large numbers of work units, i.e. the buckets 80 to 81 to 100, for example, or 101 to 120, okay? So just be aware of that. It will look different on smaller LPARs to larger LPARs. Okay, so what else can we look at? We've set an LPAR definition, and we have a number of logical processes. We think maybe the LPAR weight could be increased a little bit, the relative weight compared to the other LPARs in that KEK. We also know that the processes that we've assigned, the logical processes, have a certain polarity. Okay, so in addition to the LPAR weight, what I'd like to know is, are we actually using our processes efficiently? So let's have a look at that aspect. So efficiency means let's look at the processor polarity and the usage. What we can see here, based again on the SMF70 subtype 1 data, is the number, in this case, MIPS, dispatched on vertical high processors. That's the yellow ones. I would say efficient processors. The number of MIPS dispatched on the vertical medium processors for this time frame. That's the blue ones. That's maybe 50% shared with somebody else, okay? And of course, the vertical low processors and what's been dispatched on those logical processors. And you'll see, of course, that the peak I've just highlighted there, 11 o'clock, matches our peak that we just looked at, okay? So what we're looking at here is a view of the dispatch CPs based on the polarity of the CP, i.e. how efficient is the workload using the processes that we've defined for that LPAR. Okay, so what does this tell us in a little bit more detail? In our little Excel sheet extract here, we see our weight and our relative weight and the CP share that's been defined and the number of logical CPs. So we see that the workload, only for this day, we have to look at other days as well. And sometimes you want to look at only a portion of the day, your actual online workload, maybe from 8 until 5 p.m., not your batch workloads. It's important to define what you want to look at. In any case, for this particular example, we see that we actually are using quite a significant amount of vertical medium and vertical low processes, in addition to the vertical highs. So the vertical low processes, they're sharing cache with other LPARs, which means that when we dispatch something there and maybe have to redispatch it, we may have to do a lot of cache loading to get that data and the instructions back in there to do the work. It can be very costly in CP cycles. What that means is that the MSU cost for that workload, if it runs on inefficient processes, is going to be higher. So for exactly the same workload, you're paying more money. That's why we want to increase the efficiency. What's also interesting is to look at the number of processes we defined, in this case, the logical processes, and their status of being parked, which means when they're not being used, they're parked and they're not having anything dispatched to them. That can sometimes be a very interesting picture to look at to see how often and how many processes are being parked, logical processes, vertical low processes, okay? That can sometimes indicate that, well, we have an LPAR, we've defined 10 processes, 6 of them are vertical lows, and almost always 3 of them are parked. Well, that gives you a pretty good indicator that you can get rid of those, okay, as far as that particular workload on that particular day. So let's get back to our topology view. Now, we're no longer looking at a single LPAR, we're looking at all of the LPARs defined on this KEK. That's why it gets a little bit messy. Our LPAR that we're looking at, E001, and the vertical medium and vertical low processors, only the CPs, they're on that one chip. That's great. But we do see that other LPARs, in this case P001, also has vertical medians and lows on that chip. So it could quite be the case that workload is being dispatched from those two LPARs on those shared processes. That's the idea. And that's going to affect potentially our efficiency and increase the number of cycles. Okay, so processor efficiency is something very important because of the need for the instructions and the data to be available for the processor to execute that workload. So we can actually dig a little bit deeper and see what the cost is. And that's sometimes interesting to see. And that's based on the SMF 113 subtype 1 data, the hardware capacity statistics produced by the HIS task. So what I'd just like to show you here is what's termed finite CPI, which is basically the cycle per instruction impact for cache and also for the translate look-aside buffer misses. What I'm looking at here is only two processors. Processor 0, which is a vertical high, and processor A, 10, which is a vertical low. Now, if we look at the number of cycles per instruction, it's dramatically different. Now, any workload running on that vertical low, potentially it has to be unparked. That's going to cost a lot of cycles to actually get anything done. And that's what's going to hurt us. And that's what we want to minimize. Okay. So we've looked at our data. We think we want to change something. Now the question is, how do we change it? And how do we see what the result is? I'd like to change the LPAR weight, i.e. the relative weight compared to the other LPARs on that KEK. And I'd actually like to optimize the processor polarity because I think we could benefit. So the question is, well, what's going to happen when we do that? And how can we look at that? So back to my Excel, where we have this sample LPAR. So we see that for these 6 logical processes, 1 vertical high, 2 mediums, 3 lows, we would like to influence that. And actually, I'd like to change the number of vertical highs because we saw in our charts that a lot of the workload during this particular sample day was running on vertical medians and lows. If we change something for this LPAR, i.e. the weight, it's going to affect the other LPARs, the relative weights. You have to be very careful, okay? Now, one interesting chart, very interesting chart, is engine dispatch analysis. So again, looking at this sample LPAR, the green, 2.49, that's our CP share, which we've labeled LPAR physical processor share here. And we can see the red line, which that's the dispatch processor time, or not in processor in CPs, right? It goes above that line occasionally, actually a few times. To me, that's an indicator, my LPAR definition, together with the number of processors on that KEK, is not enough for this workload. It's more than the 2.49 CP share that I've defined. So that's a clear indicator to me. I need to look at that. And we also see other limits here in this chart as well. So this particular chart, engine dispatch analysis, is based on the RMF 70 and subtype 1 data, and also the hyperdispatch D99 subtype 14. Okay, so a lot of good information out of those two data sources. Okay, so I said I wanted to change the relative weight in order to modify that CP share. So currently, for this LPAR, the weight is 40, i.e. relative weight of 7.55%. So when I change that relative weight from 40 to 44, or rather the value from 40 to 44, I've changed the relative weight to 8.24. Not a huge difference. If I look at the number of logical CPs, I didn't touch that. We still have 6 defined. But the number of vertical highs has changed from 1 to 2. And the number of vertical mediums has decreased from 2 to 1. So that small change in relative weight has given me an additional vertical high processor, i.e., hopefully increased efficiency for my workload. And that's what I want. Okay. When I look at the other LPARs, and that's very important, their vertical highs, median, and low has not changed, and their CP shares changed by a tiny amount. So when you change one LPAR on a KEC, you have to look at all the others. Okay. Now, on the top of this Excel sheet, it says day 8 to 1700 to 5 p.m. I'm making changes to a specific KEC, an LPAR, for my expectations for the workload between 8 and 5 p.m. It may be different at night, okay? So we have to be aware of that as well. Okay, if you make a change, this is going to affect the entire time frame unless you can make this change automatically. And we'll get to that in a second. Okay, so our expectations. We expect that the CP dispatch time in CPs is now below the CP share. Maybe not exclusively, but much less. That's what we're aiming for. The chart where we looked at the CP usage relative to the LPAR weight, that should not be as bad, i.e., we've increased the weight somewhat, so we should actually be getting more of the resources that we want that LPAR to have. We've gone from one vertical high to two vertical high processes. So when we look at that distribution of workload on the polarity, the processes, we expect more to be running on the vertical highs, i.e., an improved efficiency. Now, sometimes it's quite difficult to compare 2 days, before your change and after the change, okay? So that is difficult. But the idea with this implementation and these changes is that we're increasing the efficiency, which means we're reducing the MSU cost for that workload for that LPAR. In addition, when we look at this LPAR workload after we've made these changes and we have peaks, it's interesting to look at, well, how many work units are now waiting? Has that changed? Has that improved? Are the peaks less painful than they were beforehand? That's what we also wanted to look at. So observing is very, very important after you've made a change. Okay, I'm actually quite quick, so I'm hoping there are questions. So just to summarize what I'm doing here, start small. That means don't look at all of the LPARs in a KEC or in a Sysplex. Really select one or two that you want to start with such that you can understand the workload, make the changes, and observe it, okay? Some customers, for example, that are changing their LPAR relative weights have set up specific relative weights for the workday workload, i.e. from 8 a.m. to 5 p.m., or the evening or the weekend. So look at workload over a larger period of time to determine whether what you want to change is going to be valid for the batch workload or for the weekend workload. You can use the BCPII automated or the program to automate that, i.e. you define what you want for your LPARs and then you make the change. Automated, okay? Now, we've been talking about CPs, and that's a good place to start, but don't ignore the ZIPs workload, okay? That's very important. So with the vertical load process, as I said, it's important to look at how many get parked. When you're going through the process of making changes, you want to be careful to make sure it doesn't hurt. So sometimes when you're reducing the total number of processes, because you found so many were parked, set them offline first. They're not going to be used. They're not going to hurt you, and determine whether that was the right value, okay? So a lot of observation is needed. And SMF can give you a lot of good information. So we've looked at data produced by RMF or CMF. So the 70 subtype 1, also the process topology based on the hyperdispatch, the SRM WLM record, 99 subtype 14. And if you want to look at how painful it is for vertical low or medium as far as cache misses and cycles per instruction. We can get all that information from the HIS created SMF 113 subtype 1. Okay, so that's the extent of my presentation. I hope that was good information, and I hope there are some questions. Martin, can I pass it back to you?
Yeah, thank you, John. So actually, at this point, we don't have any in the chat. I've got a question I'm going to ask you in a minute, but I'm going to say to people, now would be a good time if you have questions or comments to put them in the chat. But as there isn't one, I'm going to go ahead and ask you a question anyway, which is probably one you were expecting me to ask, which is, do you have any experience yet of the Z16 new fields in partition data report data around topology?
I would have to say that I personally have looked at Z16 data based on the 113 data, i.e. in the cache architecture, which is different to the Z15, okay? Right. So I can't say that I've looked at that particular data, so I'll have to say a pass on that. And maybe a good one to ask would be John Baker tomorrow. He's looked at some of that data as well.
Right. So in case people don't know what I'm talking about, and I have no experience with this data myself, I will say, for reasons which will become apparent in just a second. In SMF 70 subtype 1, with the appropriate Z16 support in, you get the home addresses at the logical processor level in the same way you get in 9914. However, there's one key bonus point here that's worth making. That is, 9914 will only give you the home addresses for the logical processors for the LPAR you are cutting the records from. That means two things. It means you don't know about logical processors for LPARs you're not cutting records from. So small ZOS LPARs, where you probably aren't bothering to run RMF at all, right? So this support fills in that gap, other ZOS LPARs that you're not cutting SMF records from from 9914s for. The other point, which is perhaps even more significant, is 9914 doesn't give you non-ZOS LPARs. It gives you only the ZOS LPARs you're cutting records from. So the new support is really good because it will speak to non-ZOS LPARs like, I suppose, coupling facility, probably more interestingly, IFL LPARs. So that's kind of why I was curious, John, if you actually had the experience of it. I don't, because the one set of data I've got from a Z16 customer, they apparently didn't have the RMF support on for. So yes, we know it's a Z16, we know it's model, but we don't know any of this topology information. So
yeah, very interesting question. And we do have some customers with Z16. So that would be worthwhile digging deeper into exactly that question of yours.
Right. And I'm going to say, so people who know what ERB scan and ERB show are can go spelunking into the data at the record level. Okay.
Yep. If you want to, right.
My wife, who is used to chairing conferences, said you should have some questions prepared for the speaker in case there were none. Well, that wasn't the spirit in which I'm doing this. I actually wondered if you had experience of it. Right. And we actually have a couple of other questions, one of which is mechanics. Will this presentation be available for later viewing? I think the answer is yes, because it's been recorded. And I also think the PowerPoints, probably PDFs in reality, will be available later. I think I'm going to have to check with the other chairs as to how on earth that's supposed to work. Now, my friend Stephen Hall, who showed up bang on time, as he always does, has a question, a technical question. If the spikes in vertical low usage in your example are discretionary batch, would it be better to remove the excess vertical low engines to prevent the unimportant batch spike affecting the efficiency of other partitions?
That's a very good question. Yeah, I really can't answer that. You do have your batch, and it is a low priority, but you do want to get it run at some point in time. So maybe rescheduling is an option. That's very hard to answer how it would affect the other LPARs that are sharing that processor. So I really can't answer that honestly.
Right. I think in some ways it's a bit similar to what I was saying in my session about SRB. Difficult to answer, but make sure, I suppose, make sure your weights are set correctly in the other LPARs to minimize this risk.
Yeah.
Stephen, I don't know if you want to if you're able and want to come off mute and comment on your question. If you are, feel free. Maybe I have to unmute you. It says here, ask to unmute. I have no idea if that works.
That work?
Hello, mate.
Hello. I've got a really old microphone plugged in. I didn't have a microphone last year, so I'm not even know if it was working till just now. Yeah, what was the question again?
It was your question.
Yeah. Well, the thing is, we've got a lot of little tiny LPARs which run batch jobs, and they run fast, but they don't need to. So I'm kind of in the process of taking engines away so that their batch runs longer. And that's kind of where this question comes at, that if we're just looking at the usage might not be important.
Yeah, with discretionary batch, I find it very important to look at the scheduling as well on the LPARs running on that KEC to ensure that they're not running at the same time, if at all possible. Do you know what I mean?
Oh, right. Yeah. So you mean flatten the spike through scheduling? Exactly.
Yeah.
And when you say discretionary, Stephen, you didn't use a capital D. The question is, do you mean capital D discretionary, or do you mean don't care much whether it runs or not?
Yeah, don't care much batch.
Right. Okay. Just wondered. And whoever JR is says, why don't you reduce the weight of this particular partition so they don't get the processors? I think that's probably directed at you, Stephen, but.
Well, I mean, reducing the weight won't stop them getting the processors if they're free.
Well, that's true. I mean, as always, isn't there the usual meta lesson of getting the weights right?
Yeah, unless you hard cap or system soft cap it, if there's free capacity, it will use the vertical lows. So you'll get those vertical lows being used by unimportant batch. Which is kind of where my question was about, well, why don't we just take away vertical lows and make that unimportant batch squeeze its own system and not the others?
Right. And I suppose the other point of view on this is if you have the control to stop this stuff from running full stop, that's probably better still than having it get initiated and then just
back to the scheduling point. Yeah.
Right. But that's politics, Stephen, isn't it?
It is, yes.
Otherwise known as the art of the impossible. So that's the cliche breakage there.
Thank you.
Okay, thanks, mate. Okay, are there any other questions, comments, meta chatter? Well, if not, thanks again to John and everybody. Please do use the QR code or the URL, which will have 8B on the end because this is session 8B. And we'll be back at midday UK time, and I think it's Piara who will be chairing for the next few sessions. So thank you everybody for your time.
Okay, thank you very much. Bye-bye.